So six. So currently we'll give you, so you have, let's say we say eight. Yeah, we can bring it, beginning of week 9, Tuesday week 9, and you will have one more week for the MPPT, actually 1.5 week. You can deliver the last part end of week 10, So that would be the last phase of the project. We'll do the schedule it that. This is what I taught, last class about observation and perturbation, and the other method was the incremental conductance. We talked about that one. These are the flowchart. I'm going to talk a little bit about the. More about the MPPT and how we are going to implement it. And after that, we're going to move on to the next phase. I'm not sure. Did Arnold give you the homework, simulation homework, or not?
Yes.
Did he give you? So that's the kind of start of that one, how the DC to DC converters, you need to design them. The one he gave you, you just do it by try and error. But when we teach this part, you can see, hey, maybe you can go find out how much are those PI values for that controller. You guys can go calculate it yourself. It's going to take maybe a week or two to get there, but that's what we need to talk about. So, let's start from here. You can watch them?
Yeah, I mean, this was me like futzing around with this.
I can think
So, you guys are going to select the perturbation and observation method, because this is simpler method. You select delta V, 2 volt, 3 volt, something like that for your project. I recommend you to use that one because it's easier for implementation, Use that one. But the incremental conductance is more effective and faster. But for the project, you guys are going to do both of them. They're going to give you good answer. To be kind of everybody does the same thing, you'll use the perturbation and observation. Now, let's go back. See, I draw the block diagram for you guys. How you are going to control the ID, IQ, or P and Q independently from each other, right? We draw the block diagram, we talked about it, and you are going to do it in the next phase of the project. That's what you're going to do. Let's assume you guys did it. Perfect. You're done. So what does it mean when I'm saying it's done? You have a 2 command. Either you can use a PQ command, right? P and Q command, right? Active or reactive. Or you can use the ID ref, IQ ref command, right? Because P and Q, they're going to translate simply, it's going to be like this. If you look at it, it's in the middle. If you look at it, we're going to have a P ref, Q ref, and you got the mathematical box, and you get the V value, right? And you get the IQ ref and ID ref. So basically, this part doesn't have any design. This shows some calculation. If you know how much is the P ref, how much is the Q ref, how much is the V, you can calculate ID, IQ, right? Now I want to connect this one to the MPPT algorithm, see what is going to happen. So let's look at a real system, what is going to happen. We have an inverter here, right? We have an inverter connected to a grid, right? boundary, you are sensing the current here, right? These currents and the voltage, they're going to come to a control box. See, this is what I'm talking about. This is the inverter, right? Now we're going to look at it, See, let me talk a little bit about it. This inverter includes a power module here. You can write down the part number for this one and go look at it, in Infineon website, Right now, I think it's called, Infineon. Let me see which one. Oh, on this one, it says UPEC. UPEC was the old name of this company. Now it's Infineon. Write down the part number of this one and go, this is a three-phase, basically this is this. If you look at it, it's this. And each cross is a switch with an anti-parallel die. And if you look at it here, see, this is a DC connection. You connect your DC, whatever, battery, solar, whatever you want. You connect it here. This is a DC connection. These three, they are AC outputs, DC inputs. Now, there are lots of detail here. This is a kind of bleeding resistor. I'll pass it around. You can look at it, but I want to show you what's the real system. This is the gate driver. And when I designed this one, I didn't spend time on the gate driver design. Semitron had the gate driver package for this one. So just look at this blue one. 1, 2, 3, 4, 5, 6, 7, 8. I have 8. I don't know what's the other two. But when I give you, you can read it here. It said CLO, CLCU, BLBU, ALAU. This is A up. This is this switch. A up, A low. B up, B low. C up, C low. So basically, you bring 6 PWM channel, S1 to S6. We talked about it, right? You bring it to here. This is kind of expensive way, but very, very safe, You bring the signals from your control board to the inverter, right? This is all power. This board is all power, The control signals come here, goes to the gate driver, connect to the power module, right? And the power module is going to go, this side is going to go connect to the output filter and the grid, right? That's one side. This side goes to the DC source, whatever it is, battery or solar. Here there are some, you need some, voltage like 15 volt, 24 volt, for kind of, this gate driver, they are there. But this is the inverter board. You can pass it around, you guys can look at it. Now, this is a sensing board. Look at here. This is a sensing board. These are current sensor. These 4, you can see here. How I say, if you are interested, write down the part number and check it on the lamp. Go look at the data sheet. These are current sensors. 4 current sensors. 3 for here. 1 for here. I'm measuring a DC bus current also. I'm not sure the name is there or not. No, it's just I call it I input and output. Input output. I didn't give it a name. But there are. See, the current comes to here. Basically, if you look at this is kind of expensive way to build it. The current comes here, goes to the current sensor, and goes out. You know what I'm saying? Here, the same thing, and these are voltage sensors. These are again expensive. Each of these one they worth about $40. This blue one there, each one is like $40. And this one about like a 15, based on how much current you want, but they're like a 15, 20 bucks. This one, So you measure the 3-phase voltage, you measure the 3-phase current, and just for extra measurement here, just I measure the DC bus voltage and current, right? So basically, this one doesn't do anything. This is just a measurement board, right? Now, here, if you look at it, there is some signal conditioning here. This is a active filter. Maybe you have it in the circuitry, those kind of things, op amps, those kind of things. All these things will be coming to this connector. Everything is reported here. So this one, here there's a match connector there. This is a control board. This is a TI board. This is a control board. So this connector here will be connected to this one. It will be connected to this connector here, right? So basically all the current, voltage, temperature, whatever you want to read is coming here. I put some extra design here. Look at here. These are custom, just I want to make this board general to be able to use it for everything. I don't want to use it for a fixed project. So basically, you can unplug this one. This is another signal conditioning board. For example, I don't know. You have a new project, current and voltage value. They are different. For example, one project was 208, one project is 480. Maybe you are going to work with a 1 kV. So basically, you can only change this board. You know what I'm saying? Because DSP, the TI DSP, only accept 3.3 volt. If you go more than that, you're going to kill that DSP. So basically, you make sure whatever you are bringing here, you are scaling down to 3.3 volt. So this DSP, I think this one had, I couldn't recall it exactly, but I think it has 16 A to Ds. A to Ds is an analog to digital converter, they call it. So in the real life, you have an analog signal. You sample those things, you bring it here to get it. DSP is a digital processor, right? It doesn't deal with the analog signal. So you sense your analog signals, right? You bring it here to this board. From here, it's going to go to your DSP, right? DSP does all the calculation and everything. Now you can see there is this DSP is pretty powerful DSP. It has a 14 PWM channel. But for this project, the one I gave you already is passing around, I need only 6 PWM channel. Look at here, read when I give you this one, read here. See, there is a PWM 1, PWM 2, PWM up to there is a 1, 2, 3, 4, 5, 6. Yes. So there is a 12 PWM channels. These are for the inverter, 3-phase inverter. And there are 4 more PWM. This is for like an independent PWM channel. With this one, you can drive 2 of these inverters at the same time. This is designed for motor drive, they have a back-to-back inverter. So you can with one DSP, you can drive both. So what is happening, the DSP does all the calculation, I don't know, all the crazy things. This is the control box right here. This is here. It does all those calculations, and after that, it generates the PWM signals. PWM signals through these gray connectors. There is a auto connection. This one will be connected to that inverter. So basically, my control board is completely separated from my power board, right? It's very good this way, but it's expensive. This guys also, each one is like $14. This gray one, they're like $14. Those purple one, they are like $14. The project should be really important project to spend this much money on it. But at that time, I want to have a good board for general board, purpose board. I can do whatever I want. I designed this one. So this is a control board. This is the sensing board, and inverter board is here. Inverter board is connected to the source and load. They will sense all the signals here. It sends it to the DSP board. It sends it to the DSP board here, right? DSP generate the PWM signal, send it to the inverter. So basically, this guy, that's the inverter. Let me make this one a little bigger. It got all the sensing. It could be temperature. We use this one for control. The one we are using only for control, I put here. But there are lots of fault signals. For example, they measure the temperature of the case of that IGBT. If it goes more than something, you have to shut down your circuit. You don't want to let it run because it's going to kill your inverter, right? There are tons of protection. We don't talk about those things. But it says the current and voltage is here. Now, this is a DC cap. On that inverter, I didn't put the DC caps, but if you look at the DC bus here, externally I can put my capacitors here. Right? These 2 points, they are available. These are the available points in that board. So I can connect my capacitors here, right? So this is where I'm connecting my capacitor. You can pass this to me. Now, in this case, I measured this current, right? And I measured, I don't know how to show you, this voltage. Right? This is what I have done. And it in the phase 3, you have a simple battery here, right? In phase 4, which I care, we have this. Basically, this one is going to measure I solar and V solar, right? This is the I sol and V sol, right? And what is going to happen? We do all these calculations, whatever, and we send the S1 to S6, right? This is the PWM signal going to the inverter. This is what we have in the phase 4. Now, let's think about how we are going to connect, because in the inverter box, this part we know how it does work, right? This part we know how it does work. We have a PREF, QREF, IDREF, IQREF, and the rest you know the story, right? So I want to see how I can connect these things to this. First of all, if you look at the PV curve, is like this, right? I short VO. Before getting to the MPPT algorithm, let's say we implemented the MPPT algorithm. I'm going to say inside this box, what there is inside this box. There is the MPPT algorithm, right? Which is going to get the I sol and V sol, and it's going to give me what? Vref, right? Vref is where I should go with this curve, right? So let's forget this one for now. I know how much is my Vref. 100, 200, whatever it is, right? I know how much is my Vref, so I'm not worried about this part right now. If I have my Vref, what does it mean? Yeah. Can somebody tell me? I want to have 200 volts, Vref. Basically, if you look at this capacitor, the voltage of this capacitor should be how much?
Vref.
Vref. It should become Vref at the end, right? So let's look at this capacitor. I'm talking about this middle one. I'm trying to relate how to connect this one to this. As I said, we know how this one works, right? So I have a capacitor here, this capacitor is this. Right? I sol is coming, let's say IDC is going out. Right? If I want to keep this capacitor voltage fixed, what should be the relation between I sol and IDC?
Equal.
Equal. Why?
Because for we charge, it should go up.
Mm-hmm. Let's say this is IC, right? And this is DC. And then this one is coming. This is I sol minus IC, right? And we know for capacitor, right? CdVc over dt, right? If I want my voltage be constant, how much is the dVc over dt?
0.
dVc over dt is 0, right? If Vc is a constant, so what does it mean? IC should be 0, right? IC should be 0. Now, let's think about it. If you remember, we said with the MPPT, this is the P curve. Right? We said we start from here, we are going to go step by step by step. I don't know, I think this curve is kind of far difficult. I'll put it here. We're going to go like this, right? We're going to go like this, right? So now look at here. So we are here at this point. I want to increase the voltage. right? See, my VREF, it says go to, for example, this one was 100 volt, it says go to 110, right? It says I want to, because I'm very far from here. For example, let's say this is a 200 volt, right? I'm going to go from 100 volt toward to 100 volt with a step of 10 volt, for example, right? So what is going to happen? This guy is telling me, hey, go 10 volts up. You're at 100 volts, go 10 volts up, right? So the VREF is 110. VC is 100. What should we do?
Lower IC. I mean, increase IC.
Huh?
Increase IC by decreasing IC.
Exactly. If I reduce my IDC, right? So let's say I'm here, I'm in balance point, right? I'm in 100 volt. If I'm balanced, staying here, what is going to happen? IC is going to be 0, right? The next command is saying, hey, I want 110 volt. 100 volt is not the answer, right? So the system should act such that this voltage goes up. To do that, what you should do, you should reduce IDC, right? So reducing IDC, now think about it. This bus is almost constant, right? Reducing IDC, what does it mean? Yeah, increasing resistance, but I want to hear another one. I want to connect down to this one here. What did I hear?
Increasing Q.
We decrease IDC. 100 volt. Let's say IDC was 10 amp, now it's 5 amp, for example. DDC was 100 volt. What is happening? What is happening? P is VI, right? Let's assume inverter is ideal, right? Let's say I had 100% efficient, right? P is this side here, is this voltage, right? Times this voltage. This voltage times this current, right? VR, right? I said I reduce the IDC, decreasing power, right? Now, oh, I get connected to the power somehow, right? I need to reduce my power. I need to tell my inverter, act such that the power comes down. Because see, the load is here, right? The load is here. So the inverter should somehow act to see a smaller load or bigger resistor, as you mentioned, right? So to do that, inverter say, hey, just tell me how much you want. Tell me how much you want, I'll do. I'll take care of that, right? The IDQ control we talked about, right? The big control like that now?
Let's say what the loader,
Huh?
let's say what the loader is within that, let's say 5 kilowatt.
No, you're going wrong way. You're going wrong way. You have it here. Go from here. How much power you have available? Load is over there. This is not load. This is grid, but I call it solid load. It's based on here how much you have here. You are matching here. Whatever you have here, you match it over there. So what we said we are here. 100, I don't know, 10, because this one is going up, this is the opposite way, So, yeah, well, okay, yeah, let's say this is a 10 amp. This is the IPV here, not the IDC, this is the IPV. So, we are here working at this point, right, is 100 volt. I want to increase my DC bus voltage. What should I do? I should bring down this current, right? Basically, look at here. When I'm going here, it's a little bit complicated, because IDC is going to, I short circuit is going to become more, right? But it's not going to jump. So this is we can see this is from here to here usually is 8 amps. This step maybe 0.1, 0.2 amps you go up. This one is almost constant from this step to this step, right? So you say this current is fixed, right? I want to increase my bus voltage. I'm going to reduce this one, right? This is like a pump, right? If this one is more than this one, I'm going to pump the voltage up. If this one is less than this one, I'm going to decrease this voltage, right? So basically, if I'm in this side of the curve, right, I have to reduce the voltage, right? What should I do? I should increase my IDC, right? So my point is, when you look at this system, to get to the VREF, we are receiving from the MPPT algorithm, right? VREF is coming from this algorithm, right? To get to that VREF, If we are less than that Vref, what we should do, we should reduce the P, right? Current means P, right? If the voltage is more than what we want, sorry, is less than what we want, what we should do, let me see, if the voltage is less than what we want, if this voltage is less than what we want, the power should reduce. If this voltage is more than what we want, the power should increase, right? Now, what we talked here, let me put it just here. If, I'm going to put it here, I sold more than IDC, so IC is going to be positive, so VC is going to increase, right? What is this one? What this one does mean here, P inverter, let's call it P inverter, should be what? P inverter should be less than P, right? The voltage is the same for both of them, right? The voltage here, how much is the power by solar? Is current times voltage. How much is the power of inverter? This IDC times. At the steady state, they are the same. Both of them, they are the same, you know. But in the transient, is not, right? So, if the solar power is more than P in, you are going to increase the boss voltage. If I sold is less than IDC, right? Which means P sold is less than P inverter. So IC is going to be negative, right? So we are going to decrease the. So basically, what we can do here, this P inverter is this P ref, right? Is this P ref. By changing this P ref, either reduce it or increase it. Let's say the inverter is working perfectly, right? As soon as I put my command here, my inverter is going to act and deliver that much power, right? So by changing this P ref, either increase it or decrease it, I can increase either my DC bus or decrease my DC bus, right? So basically, I can satisfy this one to either go this way or to go that way, right? Who is going to tell me which way to go? The MPPT algorithm, right? The MPPT algorithm is going to give me the Vref. It said Vref 100. Where I am right now, this is Vref. I am at 50 volts right now, right? What does it mean? MPPT is telling me what to do. It said I want 100 volts, but you are 50. What should I do? I should increase my voltage. Increasing my voltage means decreasing P in, right? P inverter, right? If I reduce my P inverter, so this one is going to go up. This one, either you can put it this way. This is a P sold. You can just put it here also. P sold, P inverter, and IC. You can do. If these two they are equal, means these two they are equal, right? This bus is not going to go anywhere. It's going to stay there. If this one is more than this one, this bus is going to reduce. If this one is more than this bus is going to go up, right? So this is as simple as this. So by controlling the inverter power, I can control my DC bus to either go up or come down, right? Now, let's see how we can translate it to control. This is how it works, right? We talked about it, how we can increase the DC bus voltage, how we can decrease the DC bus voltage, but now see how we can put it in the control loop. So we have all these things here, right? I'm going to do this. And did I talk about Q or not? When I was discussing all these things, did I talk about Q? So Q is whatever you want. For example, unity power factor, Q ref 0, right? So I didn't talk about at all about Q, how much Q I want, right? So this thing was all related to active power. So basically, here, I'm going to do this. I have my Vref, right? Vref is coming from where? Do I have enough space to see this? I have my Vref. Vref is coming from where? Tell me now. This MPPT algorithm, we talked about it, which is going to get the I solar and V solar. It's going to measure those values and tell us how much is the VRAM, right? What else should we do? We said we should compare this one to what? VDC or VC. We call it usually VDC, right? We should compare it either VSOL, we call it, or VDC, doesn't matter. They are both the same, right? How much I want to be the error here? At the steady state. I want the VDC to be ref here, right? What do you think the output of this PI controller is? So PREF, I'm not going to put the number there anymore. It's going to come out of this control loop, right? This guy is going to see the difference, pass it to a controller, and say, hey, this much PREF. That much. It's going to do it automatically. It's going to calculate. This one we usually give it 0 for unit power factor. Right? Is it clear? What I did, I want to get to this voltage. How much is my voltage? Is this much. How much error I have? This much. I pass it through a PI controller. It's going to give me the command for PREF. And do that. Right? So you add this one to the what you had before. Just instead of PREF value, in phase 3, you set the PREF value, 50 kilowatt, 10 kilowatt, whatever is in the description how much you should put there. But on phase 3, PREF, because in phase 3 we have a battery here. When we have a battery, we cannot regulate the bus anymore. Whatever is the battery voltage is battery voltage, right? But when I have a solar, I can work at any point, right? Where do I want to work? Here. This is where I want to work, right? Why? Because it will give me the maximum power generation. Okay, this is exactly what is at home and everybody is seeing for this solar panel. This is what they have. I'm not sure that it's so good or not, because you know what's happening over there now. This is exactly what is happening in all the home. In the home, the only difference is a single phase inverter. I didn't talk about single phase inverter. We did talk about it, but not a controller. Very, very similar to this one. You know, at one point, if you guys are interested, you can go, study that one yourself, or I can help you with that. But this is what you're going to do in the phase 4. Any question? I'm going to move on to the next. I said I'm going to put some documents for a space vector up. I didn't put it, okay. The space vector. I'll put one paper for the incremental conductance method, and I upload this sheet, tonight hopefully I'll do all of it, hopefully. I'll upload all of them in the website, you have it on. But this is what, I'm going to send you better, when I give you the phase 4, I'll give you a good picture of this one, I'll draw a block diagram for you guys here. And again, on your report, Arno put it there. Make sure you go through the steps, Usually, when you write a paper, I haven't written any paper for a long time, but usually the sequence is like this. You come up with the abstract, very quick. It will say what's the problem and what we did as an answer, what we did. Very quick, short. The next part, now Arnold said put everything over there, is the introduction. Introduction, you start to talk about this problem, what is the problem, what people they have done, blah, 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 those kind of things. The next part is you make experimental result. You put it there and say, this is the way I simulated, this is my control idea. Looks like it's working in simulation. And the next phase is the experimental result. Sometimes the experimental result is not possible because it's very expensive. We cannot do those kind of things. But if you can do it, it would be great. Experimental result. And after that, you say, okay, I did this thing. You get to the conclusion. Now, in the conclusion, you discuss it. What I did, and you explain, hey, before conclusion, here's another step, I forgot it. So you discuss your results. What I did this simulation, this experimental. So we saw this kind of things, and these things happen. And in conclusion, again, very short. You explain what happened. The problem was this, and we did this, and we got this good result or bad result, whatever it is, or this is the approach, The conclusion usually is short. And at the very end, you put your references. What was your references you used, in your report. So this format you should follow, for every report you're writing, every technical report. Now maybe something, I don't know, business report maybe is different, I don't know. But for technical report in engineering, this is the way you guys should go through it today. Any questions here? I think we are done with this part. Just let me make sure to see I covered everything. We are going to go to the new topic now. When you do this simulation, so here, remember, you have another loop, right? And the rest, right? We have those things. They call this one internal loop, right? And this is the external loop. Usually, not usually, for sure, the external loop should be much slower than the internal loop. Why? Can somebody tell me? So if you look at it like this, I have a voltage loop here, and I have a current loop here, and I will control blah blah, and I'm sensing current and I'm sensing voltage here. They call it internal loop, right? And external loop. This loop usually is at least 5 to 10 times slower than this one. What does it mean slower? Your changes here, you cannot change your values here faster than this one can respond, right? What you should do, look at here. So this signal, for example, should change like this. And here, if you look at this signal, it's going to go, for example, like this, like this, like this, right? This is how this system responds. If this value, this is this reference, right? And this system is going to respond like this. Now, look at here, I need this much time to get it stable, right? If I change my reference here, see the value was how much? It was here, right? It was not here. Now it's going to go and start here. If I change it here, what is going to happen? This one didn't get here. Before getting here, you're changing again your. So your system, you're changing your reference much faster than what you can catch up, right? This is what's the problem, If you change your reference faster than what you can catch up, so never ever you're going to get to that reference, right? So basically, how this reference is coming is the result of this one, right? So this one should be 10 times by rule of thumb, slower than this. Slower than this. Now when you do the simulation, you make that, with the time constant and those kind of things you put in there, If you make the voltage loop much faster than the current loop, never ever you're going to get it done, It's not going to converge. Okay. Now, if today you are a good engineer to be able to design this thing, you get a call maybe 2 to 3 times every week for a job. People, they call you to find somebody who can design this kind of thing. Job well paid, 120K, 330K, something like that, just to let you know. Just before coming to the class, I don't want to move from San Diego. That's my problem, I wish I could move, I'm exaggerating, I would say, but every month I get like 5 to 6 good calls. I'm saying lots of them I ignore, even I don't look at them. But 5 to 6 of them, they are really good calls. I'm saying good company tempt you to talk to them. I know I'm not going to move, but I want to talk to them because I'm sure I'm not going to move right now until even if GA kick me out. Yeah, maybe I start to move. But right now I'm saying but this kind of things that you guys can do. The next part, this is a very hot topic. So this is the one application. This is just solar. I went to something, I thought this is the best sense for you guys. You can get a kind of physical sense of what's happening because you see it everywhere. But this one could be an electric car. Basic is very similar to the electric car. All the changes around the command and those kind of things, how this control is going to happen, you know. If you look at electric car, when you push the gas pedal, there's no gas pedal. I don't know how it is. I don't have electric car, but I think to simulate it like a conventional car, you have a pedal, you can push it, and it's like gas pedal. What do you think you are doing?
Power.
Hmm?
Changing the power to
Changing
the
the
motor.
You're changing the PIRA. That's the inverter. There's a three-phase motor, right? Instead of this one connected to the grid, this inverter is connected to a motor, right? If you want it faster, you need more power, right? You push this pedal, basically it's changing this reference value, make it bigger. The torque is torque, not power, but they're similar. Torque and power, you know, very similar. And you change that. And I'm saying, so this one, if you learn it, you know, this is something is very needed right now in the market. You know, everybody needs it for many applications. You know, this is one application I'm talking about. This is solar. It's going to be for UPS system. It's going to be for electric car. It's going to be for SVC. It's going to be for I don't know how many applications. And at the last session of class, I talked about some of the application of this kind of power electronics and those kind of things. But there's many applications for this one. You guys are not going to be expert by one class, to be honest. You know, very simple to do this way. But if you guys you look at it, you like it, this is the start of this journey. You know, if you guys you like it, you have to work more on it. See this controller you see here, this one here. I cannot program it myself. If you know how to program this one, they call it embedded engineer, software embedded engineer. See, all this calculation has to happen here. That's another job. They look for you like this, you know. You go like that, you know. They are looking for people they can do the program. This is C programming, but you need to be able to do the program DSPs, you know. If today you guys are good, after this class I can find a job for you. To go start working over it. My point is, this is one application we talked. Now we're going to go to another one. That's a DC to DC converter, you know. And we'll start to talk about that one.
That's what I'm doing right now. Programming like a
I think most of you guys are junior or senior, am I right? Or grad, right? So you guys are going out of the school, you know. That's the reason I don't want to teach like power electronics 1 or energy conversion or power system that I'm going to teach later, you know. Those ones are going through the calculation, homeworks, problems, those kind of things. Because that one is building your base for this kind of thing. For example, energy conversion, the next course should be AC drive or machine control, you know, how to control, I don't know, permanent magnet machine, DC machine, I don't know, induction machine. That's another course I'm talking to the department, hopefully one day, maybe for 1 year from now, we'll add that one to the power course. It's going to be like this course. Now you guys know the inverter, but we go to the motor control. How you can control the motor, you know, those kind of things, you know, modeling, simulation, that one should be project based also, you know. That's what I like. I talked to the department, you know, they like to do it also, but right now we don't have resources for that to do it, you know. But this course is different from conventional course, and you can see you have 3 homeworks, I don't know, 1 final, 50% or more is project and simulation and those kind of things, you know. That was my intention to keep you guys a little bit more connected to the real world, what is happening, instead of just doing simple homework. I don't know, those kind of things. You have done it enough, you know, up to this point. The next one we're going to talk about remember I talked about a state space. I said, you have a system. I'll ask Paula to do this homework, a quick homework for this one for you guys together with MATLAB, simulate, you know. If you have, this is your system. This system could be this inverter we talked about here, could be a radar system, could be, I don't know, whatever I'm talking, you know, it's not power electronics. If this system, it has an equation, they call it x dot is equal to ax plus bu. And CPX. I don't know what y, I think we call it y. I can formulate a system to have this kind of equation. They call it a state space equation. If I can formulate my system like this, means this system is done. Whatever I want, I apply my sources to this one. Inputs, U is the input vector. X is the state vector. U is the input. Input, I don't know, inputs. I'll call it just inputs. And Y is the output. You have a system, for example, in the system we had, if you look at it, what we did here, we had the inputs was the VDC, how much VDC we have, I don't know, grid voltage, those things, they are the inputs, right? Let's say we have battery and grid voltage, right? The outputs are IDIQ, they are the state variable, right? IDIQ, they are the state variable. If I know IDIQ in that system, I can calculate anything I want in that system. You know, with those transformations, those kind of things I have, I can go calculate whatever I need, right? So at this time, I'm going to focus on how to calculate the state space equation. First for a buck converter, and after that a boost converter, just to get those equations first. Today, I don't know how far we are going to go, but that's the first thing we are going to do for the state space equation for a buck converter. Buck is the simplest circuit, right? In the power electronics we have, that's a buck, or boost. Those two, are very simple. We'll go through those ones to see how we can calculate this state equation. We call it average state space equation. Call it average state space equation. This is the, if you want to start to read it, Appendix B of the Daniel Hart book. It's a pretty good, you know, he explained it pretty well. I'm going to go through that book, you know, here. Appendix B of this book, you know, he's explaining it for, I think he's explaining it for Buck, but I'll do it for Boost also. After we do this one, we calculate the state space average model of the buck converter and boost converter. Maybe Thursday or next week, we're going to get to the control part. To go to the control part, we need to get a small signal model. A small signal model of the system. That one is going to be a little bit more back. Let me put the converter here, how the system works. We have a, I call it converter or power plant. For example, this converter, for example, is the buck converter or the boost converter or whatever, right? So what we want to do, for example, we want VDC ramp, right? I want to control the output voltage of this converter. Let's say, just I'm going to put this here, right? This is a V out. Right? So this one is going to come to block. It could be as simple as a PI, but usually for DC to DC converter, they call it compensated error amplifier. The name they put for this one is a compensated error amplifier. But could be a PI. You know what I'm saying? It still is a controller. You know, compensated error amplifier. Every DC to DC converter has this one. We call it compensated. We'll talk about it in detail, you know, later. We need to design this. The intention of this one is like a PI controller. We do it for analog circuit. You want to build it with op-amp, resistor, those kind of things. This is the second simulation. Arno is going to give you, the first simulation will give you the, you saw it already, I'm not sure or not, is a flyback converter. Did you look at that? Did you see that one? The flyback converter. There is a PI controller. If you look at it, there's a PI. PI is a DSP. See, this is the advantage of digital signal processing. You know, that PI, I gave you the equation, and you can go implement it in the DSP, right? And you build that one. You don't need to build any circuit. But if you go back 20 years ago, when the digital processor, they were not this much strong, and we didn't have a good microcontroller, they used to do everything analog. Everything was analog, you know. Analog has its good things, you know, the bandwidth is very, very wide bandwidth, it's very, very wide bandwidth compared to the digital. Because analog, you sample the signal at what rate when you're working with analog signal? At infinity, right? I mean, you have the sample at any moment, right? It's continuous. But when you go with a digital signal processor, you sample here, you do your calculation, again you do sample here. They call it sampling frequency, right? You do your calculation. So the bigger the sampling frequency, the less bandwidth, right? Why? Because you don't know what's happening in the middle, right? You're missing that part. You're assuming, hey, it's going to come through here. You know, at this point, I'm going to sample another one, do my calculation, and change my I don't know, control values, right? But the analog system is continuous. It's doing it every moment, right? The bandwidth is much wider. But they are expensive. They are difficult to design. Digital controller, they are much more flexible. And most of people now they use the digital controller. Now, we call this one compensated error amplifier. On the flyback converter you guys are working with, it's called just PI. It's called just PI, and you see the rest. The output of this one is going to give you the, I'm going to call it VC or VD. For now, let's say VC. VC is a V control. V control, right? Control signal is going to come out of this one. And after this one, you are going to have a PWM generator. Remember when I was teaching Power Electronics 1, when I was doing all this waveform, up here I put a gate here, on, off, right? And I say, hey, I don't care what is that. Just I put on, how we create that one. Just I put it on, off, right? That on, off is the output of this PWM generator. It's going to send this signal to the converter. On, off signal, right? To the switch. Turn on, turn off, turn on, turn off. So here you could have a feedback signal, like a signal conditioning or whatever, or it could be a unity feedback, right? Based on what you have. This one comes here, and this one comes here. This is a control loop for a DC to DC converter. It could be buck converter, boost converter, whatever. It could be any kind of converter. It could be flyback, could be buck boost, could be forward converter. This is in general what it is, right? Now, we'll talk about this one, what it is. There is a kind of a standard, blocks for this one. This one is a standard block. We know what are this one. In this one, there is some unknown. I have to define them, how much they are. But the block is a standard, like a PI, right? It's a KP plus KI over S, right? But I need to design KP and KI, right? Here is the same thing. If you are going to do analog circuit, it's a kind of combination of R, C, and op-amp, those kind of things. But how much R? How much C? Those things you need to design, That's a part of design. So my point is, this one, the structure is known, but you have to define the values for that structure, those parameters we have in this structure. The same thing here. Converter is the buck, boost, whatever it is, right? This is a control problem right now, right? If I can get the math model for this one, I'm done. I don't care what is the converter anymore. If I'm a mathematician, if you look at most of control guys, they know mathematics very well. They don't know that much about what's the power system and those kind of things. And they do a lot of math here inside this loop. So we need to give them a model, math model for this system. It's this. I need to give them this model, If they have this model, they don't care if it is a buck converter or is, I don't know, what should I say? Is a pot you are cooking rice in, you know what I'm saying? Just give them this model. They are going to look at this model. That's all they want to know, you know what I'm saying? This is important for them. And from this point after, they don't care what is that. They want the transfer function of this system, right? Now we're going to work on this part to get this one known. We'll get this one for this part. We do it for buck and boost converter. After we got these things, we'll come back to this model. This is the feedback. Feedback A. Back A. After we have this one, right, and we'll say what's the structure for these two, so we can put the models together. Now we'll tell you guys, hey, go design this value for this error amplifier. Go select those RC values. Or if it's a PI, go select the PI values for this one. You can go back when we finish this one. If you are interested, go look at the one fallback is a little bit more complicated to get this model. But if you are interested, do it. The next homework is going to give you is the buck converter with the analog. This guy. You know what I'm saying? Analog. Just go design that one for yourself with what I'm telling you. Right now you cannot because you don't know really how to design it. But when we go through this one, you guys go back, look at that homework, and say, oh no, I can calculate it. Or no, give me these values, RC values for this one. But I can go calculate it myself. You know, it doesn't have to be to me. I can go design it. And this is the difference between a good designer and bad designer. A good designer designs a system with a very critical damping, because quickly you're going to get to what you want to go without any overshoot, right? But a bad designer is going to get a big overshoot, right? What's the example for a big overshoot? What's the bad thing about big overshoot?
Car.
Let's go think about car, right? If the system is not critical damped or over damped, when you hit the brake, you know, you're supposed to stop there, right? If when you push the brake, there's an overshoot. What does it mean? The reference is there. For example, it's where Bryce sitting, you know, next to that, you know, camera, right? So you push the brake, but there's no overshoot. What is going to happen? You're going to go 5 meters more, and you're going to come back, right? But there is a wall. 2 meters later, there's a wall, right? You're going to hit the wall. So you're not going to go 5 meters and come back. You know, boom. You're going to hit the wall, right? This is a bad design. You know what I'm saying? This is not the control system. Just I'm trying to give you this example. You can feel it better. You know what I'm saying? What's bad things about overshoot? You know, you're going to pass your reference. Sometimes it's okay. Sometimes it's not. Right? You pass the reference, something bad is going to happen. You know, for example, if you have a current for this module, this IDIQ. I don't know. Let me see this one. How much is the current rate? This is a 100 amps module, right? Usually when there's 100 amps, the rule of thumb is to just use it for 50 amps maximum. You know what I'm saying? 50 amps, for example, if I want to design this circuit, I said, okay, the maximum value I can pass through this module is 50 amps maximum. How much is the RMS divided by square root 2? How much is it? I don't know. Let's say square root of 2 is 2, is 25 amps, you know, RMS, right? So I can have 25 amps RMS. So the reason we are doing it, we know when we design the control. You know, if you're going to go to 25 amps, I'm not going to go perfectly to 25. I'm going to have some overshoot, right? So maybe I'll go to 30 and come back to 25, right? That's fine. 30 means 70, right? 60, it means 60 because still this module is good. It's not going to burn. But if I have a bad design, right? So let's say I said I'm going to use it for 40 amps. Now I have a 150% overshoot. So this one is going to go to more than 100 amps. Boom. This one is going to blow up, right? So this is the design. I'm saying when you design this thing, you should consider all these things in the equation. You know what is going to happen if I have this much overshoot. Usually, you design it for 20% overshoot. You know, keep that one in mind. You know, if you can keep it under 20% is pretty good. It's pretty good. You know, but if you have a really bad design, you should select a 200 amps module. You know, make sure you're not going to blow it up. You know what I'm saying? So for 200 amps, you have to pay more money, right? Now, we'll get the model for this one, and after that, we talk about this one. This is very simple. This is a very simple model. This is usually we use one. The game we choose the gear 1. But if you look at this one, for example, this guy, they have a simple transfer function. For example, we have for this one, it's sensing if they have 480 volt system, right? How much is this peak? 480 times the square root of 2, right? We are bringing a phase voltage here. Just I want to show you how much gain is going to be in this circuit. So, how much is the maximum phase? Phase is going to be 480 square root 2 divided by square root of 3, and this is how much? This is a minus 480 square root 2 over square root 3. I don't know how much is this. So let's say this is 300, right? And this is minus 300, right? So peak to peak is how much? Minus is 600, right? how much voltage I can bring to my DSP? 0 to 3.3. The signal I'm bringing to my DSP is going to be 0 to 3.3. How much I have here? Minus 300 to 300. So first of all, what should I do? Let's just do this way. So let's say this 3 volt. Usually we don't go to 3.8, keep a little bit margin, you know. If something goes wrong, you know, still you don't burn your ATDs, because as soon as you burn the ATDs of the DSP, looks like you put a nail in his eyes, you know. He's not going to see anything. He cannot see anything anymore, right? The controller is going to go crazy, you know. We cannot do anything. So if it's 0 to 3, basically this signal should translate to this, right? Right? So first of all, 600 should go to how much? 300. So sorry, 3. So 600 divided by 3 is 200, right? So I should have a gain of 1 over 200. That's the first thing. I should bring this signal times by this one, right? If I do this one, it's going to be 1.5 minus 1.5, right? It still is not good.
You offset.
Offset. Get it off. You put a 1.5 here, and then do it this way. So this is your feedback loop, right? 1.5 is the offset. As soon as you get it to the DSP, so you get this signal. Here you say minus 1.5 because I want this one, right? And after that, you time it by 200. You get the you build the real signal you have. You know what I'm saying? This is what you do. To bring it in DSP into the DSP, you have to do this thing, right? Because if it's more than 3 volts, it's not going to come to the DSP, right? You have to make everything small, but when you get to the DSP, I need to do all this calculation. I cannot do away with it. I shouldn't do it 3 volts, you know, because my real voltage is 480 volts, right? I'm going to take it back to what it was, right? So this is a kind of feedback, gain feedback here for this system when you do that. But in general, we keep it simple. Either one, we don't care. We don't go with the limitation of the DSP and A to Ds, you know. We just keep it maybe 1 or whatever, K. We put a gain of K over there and make it simple, okay? Now, let's talk about the buck converter. I want to finish the buck converter. I'm going to talk about 10 minutes about what we talked, and have 1 hour to go talk about this, and we have 15 minutes. So, if you look at the buck converter, really fast, remember how the circuit is. This is the buck converter. I do the simplest case. I'll tell you why I'm saying call it simplest case. Because this inductor has what? Every inductor has a resistor, right? If you're going to make it, I'm going to give you this one in homework. You guys give me the homework. RL. Right? This guy. I'm not going to do any of this one, you know, just because the calculation is going to get crazy, you know, but you can do that home. You can spend time on it. How about that?
Yes.
How about switch? Right? There's more. You know, if you want, here there is a stray inductance, you know, but you don't go that much further down, you know, because it's going to calculation. But let's erase all those things. We go with the ideal case. No on, no on. is the VF, which is equal to VC. This is the IL VM. Before I start to calculate to model this thing, this switch has a duty cycle, right? Is on for D and is off if you look at the gate signal, right? It's gonna be like this. How much is this one? And how much is this one? So keep this one in mind. You know, we went through everything for this circuit. When the switch is on, we have one circuit, right? When the switch is off, we have another circuit, right? So when the switch is on, let's say switch is on. Let's say somehow I calculated my equation. I call it x is equal to, oh, I forgot x. X in this circuit, I'm not going to put a VCIL or ILVC, just I want to go with the same way I'm doing it. ILVC. You know, IL and current of the inductors and voltage of capacitor, they are the state variable. You know, you should know this one from circuit theory, you know. Inductor current and the capacitor voltage, they are the state variable. If I know IL and VC, this circuit is known. I know it. Now, doesn't matter if this switch is on or off, I have IL and VC. So X is not going to change, right? I have two equations. If the switch is on, X dot is equal to AX plus A1. A is a kind of dependent to the circuits. What values I have in my circuit, what values I don't have, plus B1 U. When the switch, and I have a Y, I'm just going to call it Y, or let me use the same notation. You use a VO. In this case, it's a VO, but let's use this one. VO is a C transpose. So VO, see, in this circuit, you want to know the VO, right? You want to calculate the VO, which is a VC. In this case, it's a VC. But just I'm putting it kind of to formulate this system. It's going to be CT1 times X, right? When the switch is on, I have some elements, keep in mind. We're going to have something like that. When the switch is off, right, X dot is X dot. So it's going to be A2, but the circuit is going to change. A2X plus B2U, and VO is going to be C2T times X. Right? So if the switch is on, is this. If the switch is off, is this. So tell me something I can use for any time. I don't know if the switch is on or off. This switch is switching by 50 kilohertz, right? I don't know, switch is on or off at this time. Give me an equation I can use it for any time. How? Can you tell me? Can somebody guess? Huh? So there is a switching, right? There is a switching frequency, for example, 20 kilohertz, 50 kilohertz, right? For example, if 50 kilohertz, I don't know, 1 over 50 kilohertz, how much is it there? For example, 10 millisecond. 10 millisecond, we have this circuit, right? So out of this 10 millisecond, let's say the duty cycle is 30%, for example. So 3 milliseconds, the circuit is on. 7 milliseconds, the circuit is off. 3 milliseconds, I have this one. 7 milliseconds, I have this one. What should I do? Average, exactly. See, I put it there. If I want to do, I'm going to average it out, right? How much is I have the equation up there? V. How much I have this equation down there? 1 minus D, right? So I'll put it this way. I said, this is a state, X dot is going to be A1D. A1 is a matrix, D is a percent, 30%, 40% is a scalar, right? Let's begin. Plus A2 times what? 1 minus B exactly. Times what? X. Plus, come here. How much I have B1? Plus how about C? Which is here VO basically, here in this case is the VO side. How about VO? D this one, 1 minus D this one, right? So it's going to be D CT C1, sorry, C1T and C2T. Right? So this equation is going to, I can average it out. You know, it's not going to be very accurate, right? Why? Let's say it's not accurate. If you look at the inductor current, think about it. I'm going to put forward a series. Inductor current, remember, it was like this, right? Right? You have a ripple on it, right? When it's on, it's going to go off. When it's off, it's going to come down, right? I'm telling you, hey, I cannot tell you exactly how much it is, but by this equation, I tell you it's this much. I give you average of this value, right? This method is going to give me this one. It's going to give me this one because I averaged it out, right? I averaged it out. But this is the real current. It's not going to give me the real current. They call it average method. This is the average method, you know. It's not going to go to the detail of switching, but for the control purposes, it's okay. Because this is, at the end of the day, this is the one where then, yeah, you have some little here. You're going to get there. But if the average gets there, this is what you want, right? I can control the ripple with the inductor value, with the switching frequency, right? I can reduce it. So if I can get my average where I want, so I have done my task, right? I've completed my task, right? So basically this method is going to give you this one, not this. I'm not going to push you a lot because if I want to do that one, I'll tell you to simulate a buck converter with the just regular switching, you know, just go calculate this current. Now, build a circuit, X dot equal down, right? With this method, and go plot the output. So that one is going to give you this one, the real circuit is going to give you this one, you know what I'm saying? And you can see, hey, this is happening in the reality, this is happening in math world, right? But it's good enough, why? Because I'm going to use this one for my control design, right? This is what I want to use for my control design. Because it's easier, it's much easier. That's math equation, those things are not there. Now, we have this one. I'm going to stop here, I'm not going to move further because the goal is for the buck and boost converter to get this equation. And after that, we go to the small signal. I think next class we'll finish the steady state for buck boost, and hopefully we'll get to the small signal. I'll stop here. Any questions? So if you have any question, don't leave it for the, I think today was the last day you can ask your question. You know? If you have a question, go ask him tonight, after tonight, you know? Don't leave it for later.
Yeah, that is exactly.
I'm worried about the
Okay. Let me start the average state space equation for buck and boost, and I'll give you the buck boost as a homework. You guys can work on it, you know, get the model for that one. And I don't think so. I'm going to get you a small signal model for this system or the linearization of that. Because I want to talk a little bit about the phase 3 of the project, showing some simulation. Let's see how far we can go. this phase, the phase 3 is the most difficult part of your project. And weighting wise, it's going to be 35% for phase 3, 35% for phase 4, and phase 1 and 2 already you gave it to me is 30% of your project weight. You know what I'm saying? Phase 1 and 2 was kind of very simple and basic. Phase 3 and 4, they are the ones involved with the control. Just to let you know, it's on the grading part.
Is phase one graded yet?
Yep.
Is phase one graded yet?
He said he's gonna bring it, I think today or tomorrow, or next, but he's gonna bring it for you, yes.
Quick question.
Yep.
Is it possible to have all the requirements for the project out like at the beginning? Because I know that some of the requirements were brought forth yesterday, and so some of us that are already done, like just the way that it had to be implemented. There's multiple ways that the space vector modulation could have been implemented, and certain other things.
The way I taught you here, which method did I teach you?
Well, no, there's a module in.
No, I don't. Do you want me to do you want me to do module? No. I think that one he clarified, but definitely you should know. If I want to say all the simulation you want to do, you can find it somewhere else. I don't.
Right.
So do you think you should get that one? If for example there is somebody like Reza has all this thing done, do you think me looking for it to you do it, or you go get a copy from somebody put it here? Which one do you think I'm looking for?
Well, I mean, if there's both options, I
No,
feel like
I'm saying you're instead of me. Which one do you think I'm looking for?
I would probably guess the more complex one, the full one that.
The more complex one.
The one in which we actually implement the control.
The space vector?
Yeah.
The one I taught on the board.
Right.
Which one did one of the classes I taught about the space vector, real space vector here, and I said right away this is not part of this course.
Mm-hmm.
I mentioned this is not part of this course. So basically I'm expecting you guys to do what I did on the board, right?
Right.
And if you look at if you really want to see, look at the space vector model in the PCM to see what they have done. That one is a real space vector.
Right.
No, I don't want that. Definitely I don't want that one. I want you guys to do everything by yourself. And on the running it longer, you should know this one. Because you studied it, the reason I said, just I want to tell you, hey, because the L is big and R is small, calculate the time constant of the system, right? You should go like at least 5 times of that time constant, If you just put it, a little bit longer, you will see it, because if you plot it, initially if you look at, for example, first 0.1 second, the currents, they are kind of not like a 3-phase system.
Mm-hmm.
But if you go running a little bit longer, because it's the initial value of the inductor.
I just mean on the project assignment sheet, everything that we need to discuss, it would be easier. If
No,
it was
I'm not
all-
gonna give you that.
No.
And to discuss, you should go find, do based on yourself. When you're gonna write a paper, IEEE is not gonna give you a chart to say, okay, hey, I want you to discuss this. This is up to you. You go do your research, and you say, what do I want to discuss? And if you come up very short on the discussion, you say, no, you then make what you want, what I'm saying? This is up to you guys, this is more like a research, what you are doing is like a report. I think you have seen the difference between this course and the other courses, This is for those when they're graduating, they're leaving the university, they want to go start to work for companies, do the graduate level. If you want me to give you homework, like for electronics 1, for energy conversion, hey, solve this equation, give me the answer of this one. Solve this one, no, this one is different. This one is getting, getting you guys ready for a real, when you go to the board, nobody is going to give you, I want this, discuss this for me. They give you this circuit, go run it, whatever it's bringing you, what you are thinking. believe me what you are thinking. This is when you work for a company, when you work for a university, wherever you are working, they ask you to go do your homework, work on it, and bring back what you think, what happened. This is good, this is bad, this is what we saw in the circuit. You know, that's the reason I'm not putting exactly what I want over there. I want you guys to look at it. For example, in this project, something is clear, and I kind of indirectly mentioned it in the part B. I said, keep the MA point A and compare the first harmonics. So you can discuss it more. That is clear that this one is going to be higher, because this one has a better usage of the DC bus. But this is what you need to discuss with yours. Even if I would not say, they say, hey, we did run this sign PWM, we did run this space vector PWM. This one is going to give us a higher harmonic. Or I can reduce my bus, DC bus, get the same result I'm getting from my sign PWM. These are the things you guys are going to do. You know, you're becoming engineer. You know what I'm saying? You're not anymore high school or freshman. Those things, they give you everything and okay, this one you should go bring it back. No, you have to start to think about it yourself. That's it's some part of it is intentional. What I'm doing, is intentional. I'm trying to not give you everything. I want to let you guys, you can see it in this way. I'm going to say design the system for critical damping. That's up to you guys. Go do whatever you want. I taught you the equation, critical damping. You read from the circuit theory, and go design it. Now, yes, you have to pull some of your hair. Believe me, I'll do that a lot myself when I'm working on the project. Here, look at here. Just to show you, this is yesterday. These two IEEE papers I'm working on in my own company. I'm working on this one. I have to sit down and read this thing. This is for my own homework. Just I'm saying, don't think I'm unfair to you guys. I do the same thing. I have to read everything on this one to see what they did. For example, if you look at this paper, this is the problem we have in the product. If you look at here, I don't know how much you can see here. The blue one is what they had initially. The black one you cannot see most probably. They got rid of all those distortions. Ours is not as bad as blue one, but it's not as good as the black one he has here. Because I'm doing my own homework. Nobody's going to tell me what to do. I have to go read this one. Can I use this one for my work? If I cannot, what should I change on this one to be applicable to what I'm doing over there? Okay? This is what is going to be from now. But when I see my little one is playing, I say I wish I can go back there. Because it's going to get worse and worse and worse and worse. Just to let you know, you don't think it's going to get better at all. It's going to get really worse and worse. Believe me. Some people, they like it. They think if they're more productive there, they don't look at it as worse. But me, I look at it as worse and worse. Believe me, it's going to be busy and busy and busy, more and more. It's going to be like that. Right now, most of you maybe are single, kind of, maybe you have some married one, but most of you are single or you have a girlfriend, boyfriend, Hey, as soon as you get married, it's going to get really much more difficult. But no, don't get me wrong, hey, don't get me wrong. But I'm saying it's going to be very different from what you are now. I remember I used to jog 15 miles every day. Every day. When I was doing my PhD, that wasn't just me. I come from work home, I was working full time, At 5:30 p.m. I'm in my dorm, I'll go jog 10 miles wherever I want, I'll come back. I don't care, is it 2 hours, 1 hour, how fast I'm going. Because there's nobody waiting for me over there, what I'm saying? Now as soon as this class goes to 7:30, the little one is waiting over there while you're late. I have to go answer that. I'm telling you, things are not gonna get, maybe I should think about it better than what it was before, but yeah.
You know you're on the camera, right?
I'm not saying anything wrong. She knows it all. She knows everything very well. But really, intention of these projects is you guys, you need to think more about it, especially the phase 3 and phase 4. Just I'm warning you here. You have to work really hard on that part. This is something very, very new for you guys. Those block diagrams I put here on the board, now you have to go implement those ones in your simulation model. This is a real system with a control and feedback. It's going to take lots of time. If you leave it, you are going to have 2 weeks. I'm going to give it to you tonight. I'm going to send phase 3 tonight. You have it until the next Thursday. The reason I'm saying I'm keeping 2 weeks also for phase 4, which is going to be I think end of week 9. I'm trying to finish it by end of week 9. You know, you guys week 10 you will be free. You know, you don't have to spend time on this kind of. But I may push it to the one session back. You know, to Tuesday of week 10. You know, so I don't want to leave anything for Thursday of week 10. You know, so you have only 2 weeks to work on it. You know, so work on it as hard as you can. If you build the open loop system, now you're going to get into controls. I'll show you some simulations. Let me. Yeah.
So do you have a test date for the?
Test one.
Yeah, when we're gonna test.
We're going to have only one exam, final exam and the regular time.
On the final exam day?
Yeah, I was thinking maybe we'll do it, you know, last week, last day, last session, you know, a little before the regular time, you know, when you have only one exam. Yeah, it's going to be 3 or 4 questions, you know. So let me start this block converter and boost converter because I want to talk about the phase 3 project. So we were talking about the state space average model and how we explained it. We said there are 2 cases: switch on, switch off, right? We said what we are going to do, we are going to write the state space equation for when it's on. How long is a dt, duty cycle times t, right? And how much is off, how much is it is 1 minus dt, right? And use the average. I have it for dt here, for 1 minus ddt here, right? So if it's, for example, a times 1 times dt plus, let's say, this is when the switch is closed, right? Closed. And if, for example, b times dt, see, this is not just for this one, state space, you know. I have 2 cases, 1 case here, 1 case here. If I'm going to go by average, I said, how much was here, how much was here, I'll add them together and divide it by the factor, right? So basically, you can see this one is going to go away. Whatever I have for on is going to be timed by d. Whatever I have for off is going to be timed by 1 minus d, right? So this way I'm going to get my state space equation. Now let's start with the bulk converter. And before I get started here, you know, you are using PCM, be careful what you are doing with the PCM. See, any software you are doing. Because some of these blocks, they are built and they are there, right? If you use the PCM blocks, don't come ask me why my model is not working. Because I know what PCM has done, but I'm going to say, I don't know what I taught here. You know what I'm saying? Just look at the DQ to ABC transformation. Just compare it to what we have in the class. You know what I'm saying? They are a little bit different. Fortunately, the one PCM has is not very different from what we have. But if you go, for example, with MATLAB, it's completely different. That's another way. Because the DQ axis they selected, they are different. I selected D here, Q here. I think MATLAB is selecting it this way. Q is here, D is here. You know what I'm saying? So there's not that big of a deal for somebody to understand these things. You know what I'm saying? Is go with that kind of transformation. But for you guys, if you are using the MATLAB blocks, you know what I'm saying, for like a DQ, you can write your own equation from what I gave you. It's not a big deal. You put a kind of math function, you have it, just bring the 3 inputs, for example, A, B, C, D, and theta. And just write down those equations inside these blocks. Me, personally, myself, I would like to do it that way. Because I know exactly what I'm doing inside my blocks. You know what I'm saying? Instead of going grab something from somewhere. For example, somebody was talking about, now maximum power point tracking is there's a block for that one in PC. Yes, there was a block in PC 10 years ago when I was using it. And the block was wrong. The inventor of the founder of PCM is my friend. He's a Dr. Hauji. He used to be a professor in Concordia University. He gave up university and he started his own company. And now he lives in Boston. And I called Hauji, how this one works? And we started to talk, and I figured out, for example, somebody like me, he gave me, because some of the examples is coming from you guys. You do something interesting, you can send them email, just they add it to the example list. You know what I'm saying? They can add it over there. And I told him this is not the way it should work. And we talked about it, and we figured, yes, this is wrong. And he told me, can you give me your MPPT method? I said, no, I'm not going to do that. I'm going to keep it for myself. But for example, I did another one with single phase converters, it's not there, control of those ones. My point is, don't think the PCM 99% is correct. Just like this way, don't come back anytime and say, oh, this one is wrong. No, 99% is correct. You know what I'm saying? But it may be some problem. You know what I'm saying? Just make sure what you are doing. If you are using PCM block, I cannot follow what you are saying. You have to do it yourself. But if you write my equation I taught here, if you have a question, we can talk about it. Average state space equation. We start with the buck converter. We talked about this one. The goal here is we want to design a control system. For example, to control the output voltage of the buck converter. You have a power supply in the lab. You want to be able to set your voltage reference 10 volt, 15 volt. The knob you have in all these power supplies, right? That will basically is setting the reference value, how much voltage I want in my output. 5 volt, 10 volt, 7 volt. What you are doing by changing that one is a simple potentiometer. It does change that one, it's kind of, it's scaled up. So based on that one, you say 5, 6, whatever you say. You put your reference value there. Now you have a DC to DC converter. If you look at it, all of them, they plug to the wall. If you look at it, all of them, they have a full bridge dielectrifier. If you look at it, maybe not all of them, but lots of them, they have a full bridge dielectrifier, the one we studied last quarter in the power electronics 1. And they have a capacitor as a filter to clean up that voltage. And maybe they have a transformer also. We talked about that one to bring down the voltage from 120 volt to something smaller. But basically, what they're saying a DC voltage here coming from the wall, right? AC coming through this dielectrifier and filter cleaned up. You have, for example, 30 volts here or 25 volts, whatever, based on what kind of transformer you put there. Now you have a 25 volt here. This is fixed. But you say, for example, you say 30 volt. You say, I want to have 5 volt. So you set your output voltage 5 volt. This is a buck converter, right? You have a 30 volt here. You want to have 5 volt here. For example, you have a 30 volt here. You say, I want to tell 10 volts. So you set the output on 10 volt, 15 volt. Based on what I'm saying, all of them, they have a control loop. You have to do that. Now, to design the control loop, as you saw it for the inverter, what we did here, I need to get a model for my converter, power plant. Remember we went through all these DQ equations. We went, here for RL and grid. That one was the power plant. In inverter, we assume that's ideal. In the model we put it, we say it's going to generate exactly what we want. We went through all those DQ models to get the model for the grid. And after that, we connected to the rest of the control system. You got that transfer function. You guys are going to use it for critical damping. Design your system for critical damping. What we are going to do here at the first step, we need to get a mathematical model for the converter as a power plant. We call it power plant, right? We need to get a mathematical model for the converter. And after that, we're going to go to the control loop. So control loop is going to be later. Controller, I don't know, PW generator is going to be later. Now we are going to focus on the mathematical model of the converter. The buck converter is like this. This is a V in, this is a VO, R, this is a VC, IC, VL, IL, and this is a switch. And two cases. I'm going to go this one in complete detail for this one, and the both boosters are going to go a little bit faster. We need to find the equation x dot is equal to ax plus bu for two cases. Once the switch is on, once the switch is off, right? So let's start with the case 1. Switch on. Case 1. Switch is on. So if the switch is on, what was the circuit? This one is shorted here, right? This one is going to be reverse bias, right? So this one is out. So basically the rest of circuit is going to be there. It's going to be like this. And I don't emphasize on the switch that much as I used to do on the power electronics one. The switch here for me is the ideal case, you know, it's going to be on and this one is going to be off, right? So the circuit is going to be like this. This is the output, you know, remember we said, we call it VO, even in the matrix I wrote it, you know. This is what we want to know at the end, right? We have a buck converter or whatever converter, we want to see what's the output voltage, you know. When we put 100 volt, for example, in, if I change the duty cycle here, right? If I change the duty cycle here, I want to know how much voltage I have here, right? This is what I'm looking for. Here I know I have a 20 volt source, right? I want to know when I change this one, how much I'm going to have here. Or, I want to know if I want to control this one, how much duty cycle I should have here, right? So, let's start it now. We'll write the equation here. Inductor current and capacitor voltage are the state variable. Keep in mind. Inductor current and both capacitor voltage. So we talked about x dot is equal to ax plus bu. X is, I'm not sure which one I do first, IL, I think, yes. X is IL VC. This is we call it a state vector. This is a state vector. Now let's write the equation here. The rest is simple as before we had. So a KVL here, right, and a KVL here. V in is equal to VL plus VC, right? One equation here. V in is equal to VL plus VC, right? Another equation I have here, what is that? VC is equal to VL. So, but at the end, I want to have only IL. See what I want to have in my equation. IL, VC, V in, and the rest of this value, RCL. You know what I'm saying? So VO cannot be there. You know what I'm saying? So let's start to write about it. So what is the VL? Should I replace this one with something? No, because this is, see here, I have it, right? I want to have these two terms, right? How about VO? So VC is good here, right? We have the VC here, it's good. Let's talk about the VO. What is the VO? Isn't it current coming here times R? And what is this current? IL minus IC, right? Let's write it down. So it's going to be R, IL minus R, IC. Are we good or we need to do more?
IC is equal to
We don't need, we shouldn't have an IC. It's only IL, VC, or derivative of this one. You know what I'm saying? Only IL, VC, the sources we have in the circuit, and the parameters, the elements in the circuit, R, L, C, those kind of things, right? So IC here should be replaced. So how we can replace IC? C, D, so it's going to be RC, DVC over D, right? So now, let's rewrite this equation. If this equation is said x dot, right? In this case, it's going to be what? It's going to be D over dt, IL, VC, something, right? We need to find that something. What is that something? Something times IL, VC, right? Plus something. U is the input resources. How many resources we have in this circuit? Only one, V, right? if for example, we had another b in, for example, here, somehow, I don't know how it could be, but now we're gonna have two of them, right? But because here we have only one, it's gonna be easy, right? Now let's write that equation in this format. I'm going to figure out the DIL and DVC over dt. So from the first equation, what is the DIL over dt? It's going to be, I'm going to take this one to this side, right? Divided by L, right? But I'm going to write it this way. 0 IL. Can I write this one or not? Because there is no IL, right? But here, I want to write it in the matrix form. I'm putting just 0 here, 0 times this one. You know what I'm saying? I want to have all IL VC in my equation. In first equation, I don't have IL. I put the 0 times IL, right? That's it. Plus, this one going to this side is going to be minus VC, right? Divided by L. Right? Plus 1 over LV, right? That's the first equation, right? Let's go for dVC over dt. So look at here, this part is null, so forget this part. Do not get confused. VC is equal to RIL minus RC dVC over dt. So I'm going to take this one to this side, right? Take this one to this side and divide everything by RC, right? So dVC over dt is going to be this one going there and divided by RC is going to be 1 over C IL minus 1 over RC VC plus, right, 0B. So now I can put it in that form. D over dt IL VC is going to be equal to 0 minus 1 over L, 1 over C minus 1 over RC, right, plus right. So this is the X dot. Huh? Oh, here, I missed out. Right? So this one is X dot. I call this one A1, not A. Why A1? Because we have two. One when the circuit is on, one when the circuit is off, right? I call this one A1. This is the X, right? This is the B1, and this is the U, right? Let's find out the output. How about VO? So VO is equal to what? VC, right? Right. But I need to write it in the matrix form, right? If I want to put it in the matrix form, what should I do? I need to bring the IL to this equation, right? I need to bring the IL to this equation. If you look at the here in the appendix, of the this one really is not that much important because we are not going to use this one for control at all. But this is kind of measurement. You see the result here. You know what I'm saying? You don't use this one for control. This one is says, hey, these are my parameters. I want to see them now. Just monitoring them. You know what I'm saying? So let's forget it for now because I want to focus on the control. We have that one, right? Let's go for the second part. Switch case 1, case 2. Switch is off. Right? And this is the IR this thing. Let's write the equation here. VL plus VC and the other one is said VC equal to VO, right? The second one is the same. Yes.
Yeah, it's just gonna be everything same except V is
Yeah.
0, right?
This is very simple circuit. But I'm gonna go through the steps. You know, you do the same thing for both cases. It's gonna be very similar. The V in is out. Only thing is V. So basically here it's gonna be DIL over DT plus VC equal to 0. And this one I'm gonna replace the VO with the same thing we had over there, right? It's gonna be VC is equal to RIL minus RIC, and I replace the IC with the, it's going to be RIL minus RC dVC over dt. Right? Now, from these two, I'm going to write the equation directly. I'm not going to spend time anymore on it, right? From here, I can say, there's the L here. Right? There's the L here. Let me write it one more time. This is the first time. If you write it here, it's going to be DIL over dt is equal to, I'm going to have a 0 IL plus 1 over L minus VC, and here I'm going to have dVC over dt is going to be 1 over CIL plus minus 1 over RCVC plus 0 V in plus 0 V in. Right? I add 2 0 V in. Now I can put it in the matrix form. So from this one, I'm going to say so this is a A2 and this is a B2, right? In this case, A1, A2 they are equal, but it's not. You know, we can do it for buck boost converter, buck boost converter, flyback converter. You can see these are not going to be the same, you know, or any kind of I don't know, tube converter, whatever. You know, they're not going to be the same. In this case, they are the same. And here I have only 2 elements. One here, right? 2. But if you have, for example, in tube converter, I think we had 2 inductors, right? So this matrix is going to be 3 by 3, right? You should select IL1, it's going to be IL1, IL2, VC, right? It's going to be different. It's going to be 3 parameters, you know what I'm saying? Based on how many capacitor and inductor you have in this circuit. This is the simplest one. You have 1 inductor, 1 capacitor, right? Now I'm going to go with the average method, right? Average method, we said X dot is equal to A1D plus A21 minus D, right? X plus B1D plus D2 1 minus D U, right? In this case, A1 is equal to A2, right? You can look at them. They are the same, right? A1 and A2, they are the same. So basically, how much is this one? How much is, let's call it A. Huh? In this case, A1D plus A2 times 1 minus D is going to be A, right? Either A1 or A2, right? Yeah, because see, just replace it. Then A1D plus A1 minus A1D, right? Minus A1D is going to cancel A1D, right? So it's going to be equal to A1 or A2. Let's say A1. Let's not get confused. A1. Let me see what's A now, right? How about B?
Just A1B.
A is equal to this. This is the average A we have, right? How about B?
B1D.
B is going to be B1D plus B2 times 1 minus D, right? How much is the B2?
0.
So this one, right? Because B2 is 0, right? So basically it's going to be, oh sorry, yes, B1. This is the B for this circuit. Now if I'm going to put the, write the equation, it's going to be average method, you know. Now after this one, I don't care what is the status of the switch, is on or off. Only things I want to know is D. Tell me how much is D, right? Tell me how much is D. The rest is known. So basically, D over dt, IL, just I put the average here, you know. This is not the IL and VC. This is the average of them, right? This is the average of them. Is equal to, how much is A?
A1.
Whatever it was, A1, right? So it's going to be 0, 1 over C, here, 1 over L, and minus 1 over RC, times IL DC, right? You can see D didn't appear anywhere, right? So far. But plus how much? How much is the B? Is the B1D? Where is the B1?
1
over
over
L. So it's going to be 1 over L. Actually, like this. B over L 0. This is the model is going to explain for any case, on or off, doesn't matter. Now, I'll put it in the second homework for you guys. No, this one is not the project. I'll give you a buck converter, and I want you to use it's very simple. You have buck converter, I'll give you a D value, right? For example, 50%, whatever it is. I'll give you that one, and I'll tell you to go calculate, I don't know, IL, not calculate, I want you to plot, simulate it, no, that's what I want. You go plot the VC, IL, and VO, these three, for example, right? I want you to plot these three with a real set. I'll tell you how much is the switching frequency. I tell you, for example, D2 cycle 50%. You go, this is very simple homework, but very meaningful. You understand what we are doing here. You plot that one. For example, when you plot the current for IL, this is what you are going to see. For example, IL, let's say, I don't know, let's continuous mode, right? You are going to see a current like this. Periodic current, right? Something like this. And you are going to see for VC, I don't know, you are going to see something like this. VC and VO basically, we don't need to plot the VO because VC and VO, they are the same, right? This is what you're going to see in the real circuit, right? What do you think we're going to see from this one if you solve this equation? What you're going to see for this one is going to give you IL this much, right? It's going to give you VO this much. But I want you to kind of, see. I want you to guys do it. Solve it this way and solve it that way. That way, I mean just simulation circuit, simple simulation circuit. You plot the VO and VC and IL. You will see those ones with a ripple. And you do it with this one. This is a mathematical model. This is the average. You should see this one should be exactly average of this one, right in the middle. Should be average of this one. You know what I'm saying? This is a state space averaging model you are doing. So this is a very good way for control design. Because if you are going to go with a full circuit, it's completely nonlinear. Switching is a nonlinear phenomenon, right? To model it is kind of crazy. It's going to be really difficult. But this one, you can see here. Is there any switching thing? No. Just I have a parameter D is the number, 50%, 40%. There is nothing to talk about that. You know what I'm saying? This is a very much simpler model for control algorithm design. What you will do, you design with this one, and say, oh, this is good. Now let's go test it on difference. Can we see the good things or not? If it's not good, means your model was not accurate enough. The average model you built for this one is not good enough. For example, when you do the buck converter, you do it this way, and in one of your homework, Arno is working on it, one of the labs, they're going to work on the buck converter. If it's ideal, for example, the switch doesn't have a resistor, the diode doesn't have a resistor, the inductor doesn't have a resistor, so this is the model you have, right? If everything is ideal, this is the model you have. So now, go change your model a little bit. Hey, my inductor has some resistance. My capacitor has some resistance, right? So if you use this one to control that one, most probably you're going to have a little bit issue, right? Because this model, it doesn't represent that circuit. You know what I'm saying? The circuit has a resistor. If you have a buck converter with this, you have a buck converter. This one should work with this one, but if you are going to control this one, you can use this model and control this one. But let's say, no, I give you a model like this, and I have some resistor here, right? My capacitor has, 10 milliohm. My inductor has, 20 milliohm resistor, right? This model doesn't represent this one anymore, right? When we got this model, we assumed this resistor, how much they are? They are 0. So if you are going to control this one, you should go get a mathematical model like this for this circuit, right? The one is in the appendix, it did it with RC here. The one is in the appendix calculated, there's a RC for the resistor for capacitor. Then calculated this, come up with this model. So now we have the state space model for the buck converter. I'm going to stop here. I'm not going to go further from this one. I'm going to go practice one more with the boost converter to see how we can calculate the same metrics for the boost converter. And after that, I'm going to talk about the phase 3 project. Next class, we're going to go to a small signal model of this system. Because those ones, they are going to give me the transfer function. I got this one, but it's not complete yet. I have this one. We'll talk about that one later. Let's go with the boost converter to see what is the model for the boost converter. Boost converter was like this. right? This is the model, this is the ideal boost converter, right? Let's start to write the equation for this. Two cases, switch is on, switch is off. Switch on. If switch is on, it is shorted, right? And the diode is reverse or off, right? This one is open, this one is short, right? Then you run the circuit. Right? Let's write the equation. I'm going to write 1 KVL here, right? Let's write 1 KVL here. It's going to be V in is equal to VL, right? V in is equal to AL. Let's complete this one. So VL is LDIL over DT, right? So let's find out the DIL over DT right away. You know, I'm not going to let it go there. So it's going to be DIL over DT is going to be what? DIL over DT is going to be 0 IL plus 0 VC plus 1 over L D, right? So I found the DIL over DT, right? Basically, DIL over DT is V in over L, right? Just I put these two terms, 0 IL, 0 VC. Now let's write the other equation. The other equation it says, and this is the IC, right? The other equation is said VC is equal to VR, right? Or VO, sorry, in this case, VO. Right? VC is equal to VO. How much is the VO? This is the IR. Keep the current waveform, current direction in mind. VO is IR times R, right? So basically it's RIR. How much is the IR? That's minus IC, right? So it's going to be minus RIC, right? So what about the IC? CDVC over DT, right? So it's going to be minus RC DVC over DT. So I can say DVC over DT is equal to. So do I have IL? No. So I put a 0 IL. So I should divide both sides by minus RC, right? It's going to be minus 1 over RC VC plus 0 B, right? Plus 0 B. Now I can write my matrix. So this one is 0, 0. This one is 0 minus 1 over RC, right? 0, 0, 0. Plus. Here I have 1 over L, and here I have how much? 0. Right? This is the A1. This is the B1, right? I got my A1, B1. Now, I'm gonna go for the when the switch is closed. When the switch is closed. Alrighty. Right? Switch is off. If switch is off, this one is open, right? And this one is short. So let's put on straight. It's gonna be see, I'm not changing anything in the circuit. See, for all of them, VL is here, right? It's the VL. Right? That's the same polarity I'm using. Either for this one or for that. So VL, VC, IC, VO, R, IR. Right? Now, let's write the equation. The first one. We're going to write KCL, KVL here, right? V in is equal to VL plus VC. Let's finish it here. This one is going to be L DIL over DT plus VC, right? This is good. I have a IL and I have a VC, right? Let's find the DIL over DT. It's going to be, this one should go to the other side, right? Minus VC plus V. I don't have any IL. So I'll put how much? 0 IL. Minus. VC goes to that side divided by L. It's going to be 1 over L VC. Plus 1 over L V. So one equation we have now, right? Let's go to the second equation. Again, this one is to be equal to this one, right? VC equal to VO. So VO is RIR. In this case, IR is IL minus IC, right? So it's going to be RIL minus RIC, right? So IC will replace in the CDVC over DT. So it's going to be RIL minus RCDVC over DT. So this one is going to tell me DVC over DT is going to be. This one is going to go to the other side, VC is going to come to this side, right? And divided by R. So this is RIL divided by RC is going to be 1 over C IL, right? This one is coming to this side, it's going to be minus VC divided by RC is going to be minus 1 over RC VC. What else?
0 V.
0 V. Right? Let's put it in the matrix form. So it's going to be 0 minus 1 over L. And here it's going to be 1 over C minus 1 over RC plus 1 over L 0 B. This is the A2. This is the B2. Right? Yeah. So now let's find the average model. Average model, see, if you look at here, B1 and B2, they are the same, right? Like here. So if we're going to write it here, if B1 and B2, they are the same, what's the B? It does be B1, right? So let's write it here now. I start with the B because B is easier. You know, first I start with B. Yes. B is gonna be B1D plus B2 times 1 minus B, and I said B1 is equal to B2, right? So B is gonna be B1. B is gonna be B1, right? Is it clear? Right. Now, let's go for matrix A. A is equal to A1D plus A2 times 1 minus D, right? D is a duty cycle. Remember, D is a duty cycle. So let's write it down. So D times A1. What is going to be? 0, 0, 0 minus D over R, right? Plus 1 minus D times A2. This time. 1 minus D times 0 is going to be 0, right? The next one is going to be 1 minus D minus 1 minus D over L. Am I right? Yeah, that's right. Now, here is going to be 1 minus D over C, right? And minus 1 minus D over RC. I'm sorry about this one. Forgot to turn it on. So A is equal to, let's add them together, right? 0 and 0 is 0, right? 0 and this one is going to be, right? Just I timed this one by minus, right? And 1 minus D over C, and so we have A and we have a B, right? Right? Huh? Which one?
First column, second.
Huh?
The second row, first row.
Oh, yes, you're right. Here. I didn't have it correct. Hold on. This is wrong. Minus D over RC minus 1 over RC plus D over RC. So this one is 1 over RC. So this is 1 over RC.
Minus one.
Minus.
Yeah, minus 1.
And the second row, first term should be
Yeah.
0.
Huh?
Second row, first term should be 0.
No.
Second row, first term. No. This one plus this
Oh,
one.
yeah,
right?
yeah,
This two is correct. So this is the matrix one. Have you guys used the MATLAB ever to solve the equation? This kind of thing? When I'm saying, go to MATLAB, MATLAB is really very good tool, to use, So we have this, when I told you I want to give you homework to work on it, one part you build a circuit, a block or book, whatever I give you, with a PC. And you pull up the current and dot, right? You start with the initial condition and you go 0 current for the inductor, 0 voltage for the capacitor. So, and you're gonna go, or we'll put the initial value for the capacitor or something, you know what I'm saying? You go simulate that one. It's very simple. I believe by now you guys to do that one is a piece of cake to do that one, right? But you will go do the same thing when I told you I want to see the answer of this one. you go to MATLAB, right? You define matrix A this much. You know how much is R, you know how much is C, and you know how much is L, and how much is D. For example, 0.4, right? I'll give you this number. You have your A, and you have your B, right? In MATLAB, I haven't used this for a while myself. You know, I don't know exactly what's the format. But if you have the A and B, you give it there is a one line. One line you type A, one line you type B, how much they are, and the second line I forgot what's the command. You know, boom. One command is going to give you IL and BC. You know what I'm saying? So this is the average answer you are getting. Why? Because you use these matrices, right? You plot this one. Now go plot the P symbol and they compare it together. You know, one homework, because I want you to see exactly what does this one mean. You know, I want you to do this. So we are done with the for now a state space average model up to this one, but you are not done for the control design. I'm going to stop it here today. I want to talk about the phase 3. And I give you a few steps of when you are implementing. Report is yours, but simulation, I'm going to help you a little bit, you know, how to do the simulation, you know. But writing the report, which is very important part, is you guys. You know, whatever you do is on your guys, on you guys. So let's go to big scene. Let me go open the model I have. See guys, if you guys you do only one simulation, see how many I do myself. You guys here? This is one case, you know. This is a half wave, no DQ, I don't know, right? And this is the solar verification under something, I don't know. So just I want to tell you, I do a lot of simulation myself, you know. And now we're going to go to the this one. And when I give you the third phase of the project, I put the block diagram for you. Just listen. No PLL block for you guys. You know, I'll tell you how to implement the PLL for you guys. Very simple things. You know, you don't have to do the PLL. But let me go find the new folder. Close loop, fucking that. I think the one I want. Let me see what is this one first. Yes, let's look at this one. This one was for a while. I want to do this one, you know. This is very simple, you know. Here I use the this is a piecing block. See, just look at here. Can you tell me what's the difference between the piecing block and not? Huh? Can you see it? No, it doesn't make it clear. The good things about PCM at least, you know, is using VD, VQ, The rest is exactly like we have. This one really doesn't matter that much because it's a zero component. So the good news is you can use a piecing block if you want. But still, if I am you, I use my own block. You know, I don't use a piecing block. But now, let's go back to the beginning of the DQ we started to talk about. So, look at here. I have a three-phase source here. I put some values here. I don't know, 10 times square root of 3 divided by square root of 2. This is a V line to line arm. There is value, something. I bring these three voltages to my this DQ block, right? ABC to DQ, and I have somehow I calculated my theta here. Hold on. So VAN, I'm gonna plug VAN. This is my VAN, right? So if you remember, no, VAN. Let me go back here. Click on this one. Look at here, how much is the line-to-line voltage RMS? Basically 10 is going to be the phase voltage, maximum phase voltage. See, I put a number here, right? Whatever I have here, see, think about it. Because I'm saying what I did yesterday. How much I put over it? 10 times how much? Square root of 2 over square root of 3. Other way? This 3 over 2 here?
Yeah.
Can everybody see what I'm writing here? Can you? So this is my V line RMS, right? Just I put it this way because I want to get this one. If I want to calculate my V phase maximum, how much is it? Let's say this is a V line to line RMS. If I want to get my maximum phase voltage, and if I want to find out the maximum, I should times it by the square root of 2, right? So 10 is the maximum phase voltage, right? Just I put it here because I want to have a round number, you know? Doesn't matter. Doesn't matter. Now, I'm going to put the VDVQ on. No. Look at here. The blue one is VD, the green one is VQ, right? Let me plug one more thing here. You can see both of them, they have a value, right? And then I need to get this value here. And put VD here. Okay. Let me I'm going to change this one because I want to show you how to build the PLS. Element source. And what's the frequency here? 60 hertz. 60 hertz. And this one times 2. How much is going to be? 5 times 2.
Multiplied by pi, isn't it?
No, I'm going to time it by pi. I'll tell you what. Hold on. Just give me a second. It's going to be 185. Okay. I'm going to change it for to 0, the delta value right now is 0 first. This delta is that small delta I was saying, you know, but let's run this one again. I want to see the PLL also. PLL. voltmeter. I call this one K. Let's run it again. Now, I'm going to go plot theta and VAN also. And let me make this one fence a little bit bigger. Now you can see better. So, let's look at here. What PLL does? Let's think about the PLL first. This is my source, right? PLL is going to tell me what's the phase at any time, right? How much is the phase here? How much phase is here? 90 or pi over 2. How much is pi over 2? Pi over 2 is almost 1.5, right? Let's double check. Let's make sure I'm not lying there. See, let's go here. Here, this table is going to tell you. See, I put the cursor here, right? Let's see how much is the theta. Go read the theta. 1.7. 1.7, right? So that's a pi over 2, right? So basically, this red line is telling me the phase, right? How much is the phase here? You can double check. It's going to be pi. If you check here, it's going to be 2 pi over 3. 3 pi over 4 or something like that. 4 values. 3 pi over 2. 3 pi over 2. This is 3 pi over 2, right? And here is 2 pi, right? And it does reset. Why? It can go all off, you know, adding 2 pi, 2 pi, 2 pi. But the problem when you are going to implement it in the digital signal processor, so you can use this signal or you can keep going with this one, right? Right? When is going to happen? Tell me. Somebody tell me. The number is going to get really, really big, right? And the problem is going to have an overflow in the digital signal processor, right? So basically every time we subtract 2 pi to get it there. So I'll show you a block. I show the real PLL block, but you guys are not going to do it. You know, see here, I cheated. What I did, see, what I did here, this is a, and I want you to do the same thing, see? I put the sawtooth here, and I put here, okay, 60 hertz, because I knew my grid, the voltage is 60 hertz, I put the 60 hertz. PLL is going to go find this one. You are not going to tell me the 60 hertz. By itself is going to go find that 6 hertz. And I said, go to 2 pi, right? 6.28, right? And I said, just reset it, you know? Just I build, because I know what PLL does. I don't want to get into the PLL discussion, right? Now, let's go back to this one. Look at here, guys, the VDVQ. How much is the VD? 0. Why? What? Remember I said if I line up my voltage with the Q axis, VD is going to be 0. So here you can see this one is blocking exactly here, right? So I put my VA on my Q axis. So VD is going to be 0. VQ is going to be how much? How much? Maximum phase voltage, right? You can see the word. How much is it? Oh, I didn't highlight. I didn't pick up. It's 10 volt, right? See now I want to rotate the axis here. See, this is what I'm talking. So remember, it's okay if this is a Q and D, right? If I put my V here, this one is going to happen, right? if I put my V here, right? If I put my V here, so there is a delta now, right? Let's put some delta to see what's going to happen. So what I'm doing, I'll put a little bit delta here. For example, 30 degrees. See what happened? Huh? What happened? Somebody tell me, guys, what happened? Nothing, right? Anything or nothing?
Nothing.
VQ is not 0 anymore. VT is not 0 anymore.
Right. VD is shift. Yeah, this one, see, there is a little bit shift here. PLL is going to go from this waveform is going to shift. It's not going to go up. But the way I built it here is that's the thing. But you can see this one still is in phase here. You know what I'm saying? And this one is here, right? But look at over there. The VD, VQ, they are not. The VD is not 0 anymore. VQ is not anymore the maximum. But if you do this one to the power of 2 plus VQ to the power of 2, is going to be how much? It's going to be 10. So just check to see how much it is. Here we have it. How much is VD? VD is 5, right? Minus 5 basically, right? VQ is 8.66, right? Somebody tell me, 8.66 to the power of 2 plus 25. And square root of that. So square root of VD square plus VQ square always is the maximum V phase, right? Now, if I select my axis is such that the blue one is 0, so that one is going to be 10, right? They are tied together. These two, they are tied together. If you make this one 0, the one is fixed is a 10 volt. The red one, right? This one is coming from the green, is fixed, right? So if I change the red one, if I change the blue one, so the green one has to change also, right? So this is what I said before, you know. I select my axis to be aligned with the phase A, so if that one is happening, VD is 0, my equation is going to get easier, right? So when you do your simulation, you have already phase 2 done, right? You have the sine PWM, right? Bring the current. You have IA, ID, IC to this block. And fake the PLL, like I did. And forget that delta, you don't have to put the delta over there, right? But one thing you need to make sure is correct. Let me get rid of delta. Because if this one is not correct, no way you can make your system work. You are going to make sure. See, this red line is going to be like this. You know what I'm saying? Look at here. The red line, for example, if I select this one cosine, let me show you. Let me show you here. I made a mistake and let's put 90 degree here, 30 degree here. I have the sum. See? This one doesn't represent this one anymore, right? If you go check here, you see it's not pi over 2 anymore. You know what I'm saying? So make sure your red line is going to match your grid voltage, as I had before, right? This one for sure, be careful, because if you don't put this one, that is a very simple thing. And I know lots of people, they are going to do it wrong, but even I'm saying it now several times. Make sure this one is working, right? This is a very, very simple thing to check. Basically, you are checking your PLL, your fake PLL, right? I'll show the real PLL next time, you know, when we have time to go over that. Now, we will learn the DQ system. Let's go to the control system. Close loop. Here. Look at here. This is a closed loop system. See, this is what you did in the phase 1, right? Phase 1 and phase 2. You did this one, right? With the inverter, with the battery, right? With the inductor and those kind of things, right? Yes. So you did that one. And what else you did here? This is what you did in the. you can do it different way. I don't know, min, max. This is the way I did. You know, I implemented the space vector PWM. So this one, right? So look at here. Because this is a closed loop, I don't have MA, MB, MC. But when I do the open loop, I'm going to delete that part. I'm going to, this one there, I don't care about this. You see, again, the fake PLL is here. Look at here. This is the fake PLL. So if I do this one open loop, just I put the three-phase sine wave here, right? For my MA, MBC, and MA, MB, MBC with a maximum 0.8, right? This is what I give in the homework too, right? Phase 2 of the project. And you can run it. So this is a space vector PWM. If you want to go with the sine PWM, just get rid of this part, right? Just you put MA, MB, MC, right? The sine PWM. 3 sine waveform, right? Now, you know very well how to build this one, right? You know this one, right? This is what you build. Just let's call this one MA, MB, MC. Going back to the control algorithm I taught you, the block diagram, the big block diagram, right? What I did, I measured my IABC, right? Calculated my IDIQ, right? This is what the block before I showed you, simple simulation, right? You need to verify this thing block by block. This one is working, this one is working, because you need to make sure when you are building a car, the tire is good. If the tire is flat, somehow I know it's a rectangular, you know, whatever you do, the car is not going to move, right? You should make sure your tire is good first. And after that, you start to drive the car to see how it's working, right? If this block is wrong, whatever you do, even you do the best design on the control, because it's not working with the right system, it's not going to give you a good answer, right? So now I have my PWM technique built here, right? I have my feedback circuit here. I have my PLL here, right? And this is the THT. See, there's a block in the PC. We can just calculate the THT for you. How much is it? Now, look at over there. Top one is a very important part. Let me zoom in a little bit here. Don't take a picture. You can do this thing. This is not Look at this. This is a C, QREF, PREF, right? So I put a kind of step function here, whatever I want. I don't know how much I want. You can go look at it to see how much. QREF, PREF, right? What is this? V. What is this? V. The maximum phase voltage. Somewhere I have calculated. I don't know. I'll show you very exactly. But I put it here. No, here. I put this one. Look at here. Let's click this one. Is 169.83. I think the grid is 208 for the one. Yeah, it's a 208 here. You can see, 208 divided by square root of 3 times the square root of 2 is going to be 169, 170, right? So I need this one. If you go look at the block, the first block, not the one with the decoupling, not the one that has the decoupling. So output of this one, what is that one? The top one is an ID ref. This one is an IQ ref, right? Right? The PREF, QREF is going to translate to ID ref, IQ ref, right? You guys looks like you never ever heard what. Right? It's going to be ID ref, IQ ref, right? Now there is an ID IQ, the error signal, right? And the PI controller, right? I don't have the decoupling part. If you take a picture of this one is not going to work. Or you have to put it with the decoupling circuit, right? So that's the easier version. And divided by 0.5 VDC, right? Here is going to give me EDEQ, right? Converting it back to the ABC. MAMBMC is going to come through, right? Go to this one, create my switching signal. Going to that inverter here, you can see it, right? Let's run it. And let's run it. Hopefully it's working. I didn't show you what's inside the PI value. I don't want you to take a picture of that. The first thing I'm going to do is this. See, ID ref, ID, IQ ref, IQ. Why I'm plotting this one the first? You know, whenever I do this thing, the first thing I look at is this one. See how this is the control? Can you see it? The purple one, let me change the tone here, you can see better. The purple one is IQ ref. Looks like I had 75 amps, reference here, right? Actually, I had some P ref. It translated to this much IQ ref, right? And the blue one is the ID ref, right? You can see I changed my IQ ref some point here. See, this is pretty good, there's not that much of coupling here, you can see here, right? And again, at this time, I changed my ID ref from 0 to something, right? Look at the purple and the blue, you cannot see these all hidden under the red. This is a good control system. You see? The command, the actual value, the green one, see, is tracking the purple one. It's tracking the, see, there's a little bit overshoot over there, you can see it, right? It went a little bit more than the purple one. So, now, let's look at this. I want to go with, let's look at the MA and NA limit. MA, this is like a sign. Look at here. MA is the sign. MA limit is what I built. That's a space vector. Look at here, there's difference. Did you have it in your, you should have had this one in your phase 2 project. You should have seen this one in your phase 2 project. Look at here. MA is going to 1, but this guy still has a limit. It's not, maybe 0.8, something like that, see? Still you can go up with the blue one. Even the one past the 1, still this one has a space to go up, right? One more thing that I want to show you, and you can go. I want to plot, let's do this one also, P and P ref, Q and Q ref. Remember, I had a P ref and Q ref in my system, right? This is the reason I see this one, this is because of the wattmeter I have in my circuit, it's kind of a slow measurement, Well, you can see here, this one is coming here, and again it's coming here. You can see the red one is the measurement, the blue one is the command value. You can see the word for Q also, the same thing, right? Now, let's look at this one. This is very important, meaningful. Let's say I inverter A, and I want VAN. VAN. Yeah. One more thing also. Let me get rid of this P. We're going to screen. Let me plot one more. The PLL. Remember, this is the PLL. Always I have to make sure. I'm going to just plot the A. Now, first of all, look at the blue is the VAN, right? Look at the PLL. This is something you should make sure you have it correctly, right? See, to lock it at 250. You can verify it. That's one thing. This one I put it on only for check to make sure my PLL is working correctly, right? And I say in this case, I'm sure it's going to work right because I'm cheating. I'm putting what I know it should be right. But when the real PLL, I'll show you later. When there's a real PLL. But look at this one, and somebody give me your idea. What do you see here? This is very meaningful. Do you see anything? Let's look at here. Let's talk about this one. What do you see? Because this is the first change over. You can see over there, right? IQ ref change over there. What do you see in this one?
Steady state.
No, this is a steady state. Because the transient was very small. Look at over there. There's a little bit transient over here. This is working perfect. Because I changed my command over there. I'm saying I want more or less. Look at here, look at up to here, everything is good, everything is steady state, right?
Mm-hmm.
What do you see here?
The system reacts when
The power change.
No, up here, you don't have any change. IQ ref is 100, looks like 75, and ID ref is 0. Guys, tell me what you see here. I say it maybe 100 times in this class. ID ref is 0. I think you're wrong. You should do that better anyway. ID 0. 0. How much is Q? 0. What's the power factor? Unity. So can you see the unity power factor here? Yes. Voltage are the same phase, right? Right? Well, let's check here. From this change to this change, I increase my power level, right? IQ reference up. So my power factor should still stay unity, right? Because I don't have any ID, right? Look at it. Is this still unity? Did my current increase? There is one. Look at it. Look at that. Increase my reference current, right? That one is a DQ. That is happening in the DQ system. But this is what's happening in the real system, right? Look at it here. Are they in the same phase anymore? No. There is a Q. See, this is a power factor control. You can control your power. If you want to control your power factor, you can change your ID back. ID that back, right? This is the end of project for phase 3. You get something like this.
I do well once everyone came without having probably not. I can try. Right.
Yeah, I'm taking 171b after.
I need a third class. Some random class for like physics 108, which is apparently elemental math. I don't really know.
Oh, it's not my mouse. Come on.
I don't know how much you converted.
Wow, I didn't know you could do that.
Because it's 35%.
Oh, I used to be jokes.
Oh, and that's maybe you don't want
I think you know.
Don't get even the guys, even if you go very off, I cannot even go for example, anything you want to ask them.
Yeah, you're so